Welcome to lecture number 1 of our course, Physics of Device Materials. Today we will talk about the principles of quantum mechanics. We begin a new topic, the first topic in this course. Quantum mechanics is important in modern physics because it is the foundation of everything. In particular, it is the foundation of all semiconductor physics. In this lecture, you will learn about the wave-particle duality, and how the wave-particle duality leads to the energy quantization concept. So classical physics gives us two very different types of physical objects, particles and waves. And it is intuitively clear how they differ. Particles are localized. They have well-defined position, well-defined velocity, well-defined momentum, well-defined energy. You can say at every moment of time where the particle is, how fast it moves. Given the initial position r0, a free particle at the moment of time t, moving with the velocity v, will find itself at the point v times t plus the initial position r0. Now, waves are something different. They are delocalized disturbances which spread out in space. Waves are described by something which we can call the wave function, of which you have learned in the previous course, General Physics, Physics 1051. So a wave function can have different physical meaning depending on the problem on the system at hand. It could be the pressure wave in air. It could be electric field in the electromagnetic wave. It can be the level of water on the surface, in the surface wave, etc. So a wave function is defined by its amplitude, its wave number, and its period. Wave number is related to the wavelength. Wave number is the modulus of the wave vector. The wave number has the magnitude of 2 pi divided by the wavelength, and period is 2 pi divided by the angular frequency. Yet, as we will see in this lecture, nature refuses to respect this neat division between particles and waves. Light, which we normally think of as a wave, sometimes behave as a particle. And electrons, which we normally consider as particles, sometimes electrons behave as waves. And this dual behavior is not a philosophical curiosity. It is the starting point for understanding many things related to this course. Why electrons in solids form bands? Why only certain energies are allowed? Why semiconductors conduct electricity the way they do? And how this all applies to real semiconductor devices such as diodes and MOSFETs. So by the end of this lecture, you will see how the breakdown of the classical particle wave picture leads directly to energy quantization. All right, so now let's keep moving. The first indication that waves have particle-like properties came around the year 1900, when people tried to understand the black body radiation. Now, what is a black body? A black body is an object which absorbs 100% of incident light. Okay? No reflection. But of course, black bodies are not found in nature. Like complete 100% absorbing objects do not exist in nature. But many objects can be approximated as black body to a high degree of accuracy. So it is a physical idealization. It is an idealized object, which approximates many objects that really exist in nature. Now, the fact that an object absorbs 100% of the incident radiation does not prevent this object from being able to emit radiation. So think of a wire through which current is flowing. The wire gets hotter and hotter due to ohmic heating. And it eventually becomes red. It starts emitting light. This is thermal radiation. Or you can think about the sun. As the sun can be approximated as a black body. You can, surprisingly. And yet, sun gives us all the light that we need. All right. So now, when people try to understand the black body spectrum can measure. So now the spectrum tells us, a radiation spectrum tells us how much energy is emitted per unit frequency interval or per unit wavelength interval. And so the black body spectrum depends on temperature. This plot shows us how the black body spectrum depends on temperature as a function of the black body of the radiation wavelength. So at low temperatures, you have low radiation, but then you increase the temperature, the peak of the spectrum shifts to the shorter wavelengths, and of course, the height of the peak gets bigger. All attempts to understand black body spectrum using classical electrodynamics failed. They led to something which we call ultraviolet divergence or ultraviolet catastrophe, which simply means that at short wavelengths, that is ultraviolet part of the spectrum, the energy becomes infinite as you decrease. So as you decrease the wavelength. And this is physically absurd. This is impossible. Now the solution came from the German physicist Max Planck, who postulated as an act of despair, because he tried all other explanations and they all failed. So he postulated that light is emitted in discrete chunks of energy, which he called quanta. We call them photons. So light quanta are called photons. And the energy of a single photon is related to its frequency as direct proportionality. Energy is frequency multiplied with some constant, which we call now Planck's constant. And of course, Max Planck was a modest man. He didn't name a constant in his own honor. So energy is Planck's constant h times the frequency f. Or if you prefer to use angular frequency, omega, then you use the so-called reduced Planck's constant h bar. These are the experimental values. And now, based on this assumption, Max Planck was able to quantitatively describe black body radiation spectrum. And his formula, now known as Planck's formula, perfectly fits the experimental results. From this fit, he was able to deduce the value of this constant h, which in C units is 6.63 10 to the negative 34th joule second. But in this course, we will prefer to use instead of C units, instead of joules, we will prefer to use the electron volts as a unit of energy. Let me remind you, 1 electron volt is the energy acquired by an elementary charge, 1.602 10 to the negative 19th coulombs, when it goes through a potential difference of 1 volt. So 1 electron volt is 1.602 10 to the negative 19th joules. So in electron volts, Planck's constant is 4.14 10 to the negative 15th electron volt seconds. Reduced Planck's constant is particularly easy to remember in C units. It is 1.055. So basically 10 to the negative 34th joule second, or 6.58 10 to the negative 16th electron volt second. All right. Okay, so that was good and nice. Then the second evidence came, photoelectric effect. Now, photoelectric effect works like this. Light is incident on the surface of a metal. And light kicks out electrons out of that surface. Electrons fly out. Now, you call the surface which emits electrons, we call it the cathode. Then we can use another electrode, another metal, which we call the anode. And that anode will collect electrons emitted by the cathode under the influence, under the effect of light. You can apply voltage between the anode and the cathode, and that's your simplest diode. Oh, and you place the cathode and the anode into evacuated glass bulb tube. So that's your simplest diode. Now, the current voltage curve of this device looks like this. Initially, so this is the current collected by the anode as a function of voltage applied between the anode and the cathode. When the voltage on the anode is large and negative, remember that electrons are negatively charged, so electrons are repelled by the anode because the potential on the anode is more negative than on the cathode. So there is no current collected by the anode. Now you increase the voltage on the anode, and at some rather small but measurable negative value, current starts to increase. You call this voltage the stopping voltage. And it turns out experimentally that the stopping voltage is proportional to the frequency of the incident light, not proportional to the intensity of the incident light, but proportional to the frequency. So it is some sort of a threshold process. You increase the voltage on the anode above the stopping value, the current initially increases, and then it saturates. Why does it saturate? Well, the answer is this. Let's say the incident light kicks out 1 billion electrons per second from the cathode. The number of electrons collected by the anode per second cannot be bigger than that 1 billion, right? So hence the saturation. The anode cannot collect more electrons per unit time than the cathode emits. So hence the saturation. And the saturation current is proportional to the intensity of the incident light. So that's another interesting observation. So the stopping voltage is proportional to the frequency of the incident light, as the third diagram shows, and the intensity is the saturation current is proportional to the intensity of the incident light. The theory of photoelectric effect was developed by none other but Albert Einstein himself, who published a paper in the year 1905, his miraculous year, when he published groundbreaking papers on many fields, on many questions. So one paper was photoelectric effect, and he published a paper on Brownian motion, diffusion, and the third paper was about relativity. Anyway, so we have back to photoelectric effect. So here is the idea of Albert Einstein, correct idea. An electron exists inside the metal. It doesn't go out. Why? Because there is a potential barrier that the electron needs to overcome in order to get out of the metal. And so let's call this potential barrier the work function. It is the minimal energy that needs to be given to an electron in order to kick it out of the metal. Now, we agree with Max Planck and say that the energy carried by a single photon is proportional to its frequency. So energy of a photon is h, Planck's constant, times the frequency of the photon, assuming that the light is monochromatic. Yeah, I should have said this. The light is monochromatic, which means that the light consists of photons of just one frequency. Now, if the energy of the of the photon is higher than the work function, that is the minimal energy needed to kick out an electron from the metal, then that electron will have kinetic energy given by the difference of the energy it received from the photon, h times f, minus the energy it has spent in order to get out, the work function w. So this is the kinetic energy of the electron. So now, since our electrons already have some kinetic energy, hf minus w, then those electrons will be moving towards the anode and will reach the anode if the voltage on the anode is zero. Right? So you need to apply a slightly negative potential on the anode in order to prevent the electron from reaching the anode, to repel the electron from the anode. And this slightly negative potential is the stopping voltage. It is the voltage, negative voltage, at which the current on the anode stops. And the stopping voltage is the ratio of the initial kinetic energy of the electron, hf minus w, but to the elementary charge, E. In our convention, in this course, the charge of the electron is negative elementary charge, negative E. Elementary charge is 1.602, 10 to the negative 19th coulombs. All right. So we have explained the linear relation between the stopping voltage and the frequency of the monochromatic light in photoelectric effect. Because if you replace the kinetic energy here with the expression for energy in terms of the frequency of the light, hf minus w, you find that the stopping voltage is proportional to the frequency of the incident light. And so you can get this, you can collect the experimental data, stopping voltage versus frequency, try light of different frequencies, collect the experimental data. So let's say these are these points on this plot. I have made this kind of experimental curve myself. I made this up, so just to illustrate the idea. And you fit this with a straight line. The slope of this straight line is the ratio of Planck's constant to elementary charge. So here you can determine Planck's constant in a way which differs from what Max Planck has done. You have two completely different experiments. Experiment number one, use black body radiation spectrum, fit it with Planck's formula. Find Planck's constant as a fit parameter. Experiment number two, measure the stopping voltage in photoelectric effect as a function of frequency of monochromatic light. And the amazing thing that two completely different measurements give identical results for Planck's constant, identical up to experimental inaccuracy. So when two completely different experiments produce the same result for a particular parameter, then this means that the interpretation, and you have the same interpretation of these experiments. The interpretation is based on the idea that light propagates as chunks of energy, as quanta, as photons. Then this particle picture of light must be correct. Let's keep moving. So those photons carry energy. But particles carry not only energy, they also carry momentum. And the relation between momentum of a photon and its wavelength has been established a little bit later by Arthur Compton, who studied scattering of X-rays, this very high energy photons, by electrons in various substances, in paraffins. And he discovered that if you analyze the wavelength of the scattered photons as a function of angle of scattering, then the wavelength turns out to be shifted to the longer wavelength part of the spectrum relative to the incident photons. So scattered photons have lower frequency and longer wavelength, and this shift depends on the angle of scattering. The interpretation developed by Compton was that the incident photons give not only energy but also momentum to the electrons that they interact with. And he was able to produce a theory based on simple energy momentum considerations, whose main assumption is that the photons carry energy given by the ratio of Planck's constant to the wavelength lambda of the photons. And of course, for this theory, Otto Compton got a Nobel Prize, deservedly so. Then only 1 year later, a French physicist, Louis de Broglie, generalized Compton's formula and said, well, let's use it to all other objects. Why just restrict ourselves with photons? And now I'm talking about the wave properties of particles. So Louis de Broglie said, well, this momentum wavelength formula applies to all free particles. A free particle behaves as a wave whose wavelength is given by the ratio of Planck's constant to its momentum. You can relate, since the momentum is related to the kinetic energy of the particle by a well-known expression. Kinetic energy is momentum squared divided by twice the mass of a particle. So the momentum is square root of twice the mass times the kinetic energy. So you can relate the wavelength to the kinetic energy of the particle like so. Planck's constant over the square root of double mass and the kinetic energy. Now, if you plug in some simple numbers, let's say the kinetic energy of an electron is 10 electron volts, then you will find, you use the value of Planck's constant, 6.6, 10 to the negative 34. Electron mass is 9.1, 10 to the negative 31st kilograms. Let's take kinetic energy to be 10 electron volts. The wavelength is of the order of 4 angstroms, which is the size of the lattice constant. Separation between atoms in a typical solid, a few angstroms. 1 angstrom is 10 to the negative 10th meters. So, a prediction that we can make based on this de Broglie's theory. A crystal can act as a diffraction grating for electrons, having reasonable energy. Like, in order to produce an electron with the energy of 10 electron volts, all you need to do is to let the electron go through a potential difference of 10 volts. That's a couple of AAA batteries, maybe 4, 5, or 6. That's easy. Now, you can send a beam of those electrons onto the surface of a crystal and look at the reflected electrons. And if this wave picture of electrons is correct, then you should be able to see the diffraction of electrons reflected by a crystalline surface. And this is exactly what has been done by two American, I believe, physicists, Davison and Germer, in 1925, so 1 year after de Broglie's prediction. This is exactly what they did, and they confirmed this theory, this wave picture of electrons, experimentally. Now, how can we? What other predictions can be made based on the wave picture of particles. One such prediction, as promised in the beginning of this lecture, is energy quantization of particles. So a particle in confinement cannot have arbitrary energies according to quantum mechanics. Its energies must be quantized. So the energy spectrum is not continuous. The energies are not arbitrary. Energies are discrete. A particle, let's say an electron, in confinement can have only discrete energy values. And let me show you how this works on two examples. Example number one, an electron bounces between two parallel walls. Now, a classical electron can go slow, can go fast, slow, fast. Yeah? But if we apply this wave picture of electrons, of particles, then we must conclude that the wave, this electron wave, I will speak about electrons for the sake of concreteness. So this electron wave can only exist as a standing wave between two walls, just like when you pluck a guitar string. The oscillation pattern of the string is a standing wave oscillation pattern. It is such that the distance between the two walls can accommodate an integer multiple of wavelength divided by 2, integer multiple of half wavelength. So in the lowest energy state, it is half the wavelength. Next, you can have one full wavelength between two walls, 3/2 the wavelength, and so forth. So this is the resonance condition. The distance between the walls is the wavelength divided by 2 times an integer number n, positive integer number, n equal 1, 2, 3, and so forth. But now the wavelength is related to energy by Planck's constant divided by square root over twice the mass times the kinetic energy. Now plug in this expression for the wavelength into the resonance condition. Distance between the walls d is n lambda over 2, and solve for energy. And recall that energy is momentum. Yeah, solve for energy. You will find it's a simple calculation, one-liner. You will find that the energy is an integer number n, 1, 2, 3, and so forth, multiplied with some sort of a constant, which in this case is Planck's constant squared divided by 8 times the mass of the particle, and the distance squared between the two walls. So this is one example of energy quantization. Another example is a particle moving on a circle. If a particle moves on a circle of radius r, it moves as a wave. Yeah. After the particle makes one full rotation, the particle wave must coincide with itself. It must match itself, because otherwise this wave would extinguish itself. So it's again some sort of a standing wave. So this means that the circumference length. So in other words, the phase of this wave must change by an integer multiple of 2 pi. The circumference length of the circle must accommodate an integer multiple of the wavelength in order for the phase of the wave to change by an integer multiple of 2 pi. The circumference length is 2 pi times the radius r of the circle. And this must be equal to the wavelength lambda times an integer number n, which can assume a positive integer value, 1, 2, 3, and so forth. Again, recalling that the wavelength is related to the energy, kinetic energy, by this de Broglie relation. And solving for the kinetic energy, we again find that the energy is integer squared, n squared times a number. And this number has a similar structure as before, as a particle between two walls. So we have Planck's constant squared in the numerator divided by, well, a constant, which in this case is 8 times pi squared. Then we have mass of the particle in the denominator and the radius squared, like distance squared in the first example and radius squared in the second example. So that's all that I wanted to tell you for now in this first lecture. Thank you for your kind attention. I'll see you in class.